I'm Tim Ventura, and we're joined today by John Bicknell and Tim Haynie to discuss space domain awareness and their vision to use artificial intelligence and complex data mining to help safeguard our national security in space. John Bicknell is a national security thought leader and analytics visionary who's written extensively on national security matters related to information warfare, critical infrastructure defense, and space situational awareness. His extensive career experience includes roles with More Cowbell, ACT, Corious, Kronos, and other notable corporations. John's public service includes 20 years with the United States Marine Corps, retiring at the rank of lieutenant colonel after service, including notable roles in Afghanistan and at the Pentagon. He's a member of the Military Operations Research Society and InfraGard, vice president of the Information Professionals Association, and host of the Cognitive Crucible podcast. John has a master's degree from the Naval Postgraduate School, emphasizing econometrics and operations research. Tim Haynie is an IT professional with experience in remote sensing data systems for emerging sensor technologies. His corporate career experience includes roles at Spectrobotics and Data Tactics Corporation, and his public service includes over 20 years of experience in space systems operations with the U.S. Army. He has a Master's of Science in Space Systems from American Military University and a Bachelor's of Arts in Economics from Virginia Military Institute. So, John and Tim, welcome both of you gentlemen. Thank you so much for joining us today. I want to start out with POMAT, or the Pattern of Maneuvers Toolkit. What is it, and what inspired you to develop it?
Hey, thanks, Tim. It's great to talk about POMAT and great to talk about how we got involved with the DoD, even though we have, both of us, John and I, had this extensive DoD background. Our careers were there. Neither of us really wanted to find ourselves back here. We wanted to go off into the big world and do great things. But one of the things that commercial does really well that DoD is struggling with is innovation. So companies like ours that are, we got out of the military, we wanted to go off and do great things. And part of that is to enter the innovation world. The DoD kind of caught wind of that and said, hey guys, not just us, but lots of people, we're looking for great technology. We're looking for great solutions out there that could be applied to problems we have today that we can't build fast enough. And you guys can. But like any innovation company, John's and mine, we're a little bit risky, and the government is really risk averse, trying to invest tax dollars into ventures or technologies that may not work out so well. So they've cracked the code on how to do that, I believe. So each of the services, the Air Force, the Army, the Navy, they all have these sort of innovation programs that allows funding to go to companies like ours to build small products at first. And then as you show your worth and show your value and utility, you start to scale that out. And that's exactly how we landed here. We saw an announcement looking for interesting technologies to solve DoD problems. John called me and said, hey, I've got a great idea to work on a space problem. Would you like to be involved in this? And then we submitted our proposal. It went through the SBIR, the Small Business Innovation Research Program, got funded for phase one, and then they liked the products that were being built, and so funded us for phase two to build POMAT. And I'll pause there for a second, John, if you want to kind of pile on that. How did you end up here?
Yeah, that's right. Yeah, well, like Tim said, and thanks again, other Tim Ventura, for having us on your forum here. But
Oh, yeah, absolutely.
Tim and I, we got linked up back in the 2019 timeframe on another Air Force related project, and we've stayed in touch, and it's been a great collaboration ever since late 2019. But when we got in touch with the Space Force and what they wanted us to combine our technologies and build for them, this POMAT, the Pattern of Maneuver Toolkit, helps fill a void in what the Space Force needs related to being able to understand what are satellites doing on orbit, what are they likely to do next, so that they can use that information for everything from flight safety planning, planning their maneuvers, all the way to getting ahead of and staying ahead of what adversaries are doing on orbit, so that they can plan their operations accordingly.
Yeah. Now, what you guys are developing, this is technically complex. I've been going through this for, the interview, trying to write notes and good questions. And I think it is a brilliant idea. What you guys are doing is absolutely brilliant. It is technically complex, though. So let me do this. I want to do a slideshow. You gentlemen have graciously provided me with a slideshow that I can put up here. And so this is the POMAT, the pattern of maneuver analysis tool. And so I'm wondering, could you guys tell me a little bit about this?
Absolutely. So John's technology derives patterns of life. So it takes a lot of information and figures out what are the sequences that events occur. My technology says, hey, give me a whole bunch of information data, remotely sensed data about where things are, and I can take that in that stream and break it up into patterns. So that's kind of where our two technologies come together. I find the patterns, and then he figures out what's the sequence that they occur in. And if we understand what the sequence is, we can start to recognize what these patterns represent. And we'll go into a little more detail using some other analogies here. But essentially what we're trying to do is get a much better picture of what's going on in space, because in space, everything has to be done with remote sensing. And you never know where anything is. You only know where it was. So predicting where something is, predicting what something is going to do is extremely difficult because we have to do it from tens of thousands of kilometers away. And with technologies that are, sort of, there's new and emerging technologies that are good, but a lot of these are legacy systems that use telescopes and radars. And a lot of the data that comes out of that, it's got some challenges.
Yeah, I can definitely imagine. It's probably kind of a mishmash of legacy systems, right? Lots of different inputs and everything is kind of squished together. And so you're trying to decipher that. Well, so let me go to the next slide then. So why POMAT? And I think you had some notes that you wanted to provide on this as well, right?
Right. So like in the business world, like in any innovation space, you start with the problem, right? That's the whole reason we're here, is to solve a problem. The problem the DoD has, and everybody has this around the world. Number one, space is growing, all right, almost exponentially. There are so many commercial ventures out there for rides to space on rocket bodies, or putting new technologies in low Earth orbits and new communication. It's just growing faster than we can really keep up with it. So for the DoD to be able to do their mission, which is to protect our national assets and protect some very high value assets, and also understand more about our world and how things happen, they're concerned that the number of objects that are going up, that it's becoming a more complex environment than they can manage. So the more predictive they can be, the more descriptive they can be about activities and priorities, is another big concern for them. Then the more they know how to plan it and provide the appropriate response. John, I'll give you a chance to jump in on that one too.
Yeah, and back to the top where Tim was talking about how small innovative companies like ours are doing things that the government needs. The pace of innovation these days in the private sector is going beyond what the government currently has within their capability set. And so the Space Force and lots of organizations, it's not just the Space Force, but lots of organizations within our national security and government establishments are still using like really old technologies, or they're still using Excel spreadsheets to manage their operations. And that's no different for the Space Force. And so part of this capability is to like automate a lot of routine tasks which can be automated. And so it's multi-layered as far as the benefits this is providing to the Space Force.
Yeah. Well, now, if I could jump in really quick, and again, when I was going through this slideshow before the show, one of the things that jumped out at me in your literature and in the bios and everything that you've written is patterns of life, and this keeps coming back over and over again in everything that you've written. And so my interpretation of that, and I could be wrong, you guys definitely correct me if I'm wrong, but you guys are looking at the way that satellites and different things that are in orbit, different things that are in space, the way they behave over long periods of time on a regular basis. And so presumably, if you have a satellite that goes by every 24 hours and it passes a piece of space junk and it does it the same time, the same day, the same place, that's the kind of stuff that you guys are going to be recording, documenting, and pulling trends out of, right?
That's correct.
And if I may, Tim, maybe this is a good opportunity just to talk about the underlying technology for the pattern of life portion of this. It's called process mining, and it was developed originally in the Netherlands over about 20 years ago now. And maybe 18 years ago, it started making an exit from academia into the commercial world, and it started becoming adopted in Northwestern Europe in the manufacturing sector. But process mining is kind of what it sounds like. It is a way of originally for businesses to analyze the system data that all business systems produce. So you've got an ERP system, a CRM system, a human resources management system, a system that governs the manufacturing processes. All of these systems produce what are called event logs. And the event logs are descriptions of the activities that are part of the system. And so they represent user, like individual people activities or machine activities that are part of business processes. And so what process mining does is it interrogates those event logs and surfaces up process models which describe the process that is happening. And so those are patterns of life in a business context. And so what we're doing is we're taking that exact same capability, except instead of applying it to administrative business processes, we're applying it to emergent and self-organizing processes as we're describing here in this project. In this case, they're space ecosystems, but it is very much like you described, Tim, just a moment ago.
Yeah.
So the great thing about space is it's constrained by physics, right? We understand how orbits work. We understand how to describe orbits. We understand the space environment. So it's an ideal training ground for building, improving, and innovating over the technology we built, because we know that practically everything in space follows a pattern, right? Nothing happens without some action-reaction type relationship. So space, the sun puts out a solar event. And so then that bumps around a bunch of satellites, and now they have to move back to where they should be. Or someone says, hey, I'm in the wrong slot in the geo belt, and I'm DirecTV, and so now I want to put more channels over the West Coast. So they're going to move their satellite to the West Coast, and they physically have to move it with their thrusters and such, and they have to change their orbit planes. So it's the ideal environment for the type of data that's collected, the type of services that John and I provide, to be able to understand what these patterns mean, and then be able to put them into this logical sequence that teaches us how they behave and how they're going to behave under certain circumstances.
Okay, yeah. So that's the identify and predict. And then when that behavior doesn't match the expectations, that's when the threats emerge in that final.
That's absolutely right. And one of the big problems that the DoD has with so many systems is being able to understand what are the important high priority events versus the more mundane sort of routine, this is just how we do things, So, with limited number of man hours we can dedicate to this. So the more automation that's in place to identify where these alerts are about to occur, or where the more interesting patterns of behaviors that are playing out are occurring, then that enables them to focus their attention in the right places.
Yeah. So let's move on to the next slide then. And this is the pattern detection example. Now, this one, you guys are going to have to walk me through this. I've actually gone through this 2 or 3 times, and I don't fully understand. Is there kind of a layperson's way that you could explain what's going on here?
Absolutely. So remember, I said space is very constrained. So we use an intersection like this that you would find in any road in any town in America. to describe, how we sort of identify these patterns and what we can learn from these patterns. So you can, if you think about space or think about the roads sort of lay out where you can go and in what sequence you can perform these activities, because those are the rules of the road. So each of these, you can imagine a car sort of approaching the intersection, and all of us drive cars. So we kind of exhibit the same patterns of behavior when we want to do certain things. So for example, pattern number 3A, right? It's coming in at a constant speed. That's the one triangles you see that are sort of gray and moving sort of right to left here. Then it decelerates and then it stops. That's the typical pattern when a car comes to an intersection, it's got a red light, it can't move. Whereas pattern 2 here is a car that has a green light, for example. It can come in at a, or let's say it's a yellow light. It's even more interesting. It's coming in at a regular constant rate. It sees the yellow light, it accelerates because it doesn't want to get stuck by the red light, and then it goes back to its constant. Or even number 3 over here, I want to execute a left turn. So then I'm going to constant rate, decelerate, stop, and then accelerate through the turn. So all of these patterns that the cars represent are very similar to how satellites go about their daily life. That's the connection between the two. Every one of them goes through a sequence of events in a certain order in order to perform a certain mission. So if it's a comm satellite that's, that has to move its slot, if it's a weather satellite that's got to move its location because it needs to focus on a weather event that we need more eyes on, they have to go through certain patterns in order to get there. They have to go through certain actions in the right sequence to get there. And over time, right, we have enough observation data, we can start to cut these up into these specific patterns and put them in sequence. Did that get your, does that describe it well enough for you, Tim?
Yeah, that does make sense. Yeah, and so this is kind of an overhead view of a traffic intersection. And I guess I could imagine if you were looking at that, you look at vehicles coming into that, even though they're different vehicles, they're coming and going to different places, they're going to follow the same behavior patterns, right? And so, and
I think, Tim, if you could advance to the next slide, that would
absolutely. Let's
helpful.
go on to the next one. So the observations to event logs. And again, if you could help me decipher this one. So it looks like, again, we've got our intersection here. It looks like what you're doing is kind of abstracting these behaviors, and then these would represent what's stored in an event log in the time interval part on the right, right?
That's correct. When you lay down a time grid to it, you can establish sort of a time metric, or a start and a stop point. That's a critical piece of information that sort of grounds these patterns into some reference frame for us to understand, when things occur, when they don't occur, what's the break point between the events. And then here's where it gets really interesting, Tim. What happens when the patterns change? Because this is just representative of sort of perfect conditions, right? But what if we start to notice that these decelerations or these accelerations are taking longer or shorter time, right? So it used to take just a few seconds, or maybe a car was going to decelerate in about 100 feet, and now it's decelerating in 200 feet. What could we learn from that? What does that tell us about the road conditions? What does it tell us about the type of vehicle it is? What does it tell us about the maybe what the light sequence is there at the intersection? And that's what the DoD is really starting to get interested in. Not just that it did something, but how does what it did or what it's about to do, how does that fit in the bigger context of things? What else can be learned below the surface, so to speak, that gives us more information about the object that we have to observe using remote sensing from very large distances? We want to always learn more.
Yeah, well, and one of the things that jumps out at me, many years ago, I worked for the phone company, and so we had logs that were similar to, I think, what you're displaying here. I think one thing the audience should keep in mind is you guys are probably looking at massively multi-parallel data streams, right? So it's not just 3A, 3B, 3C. You're probably looking at, Lord only knows, 10,000 different streams at once, right? So.
Well, you can slice and dice this even more, right? So each of these patterns represents a car, but each intersection has its own pattern of life. Each road system has its own pattern of life. Each driveway in a neighborhood has its own pattern of life. And that's kind of where we're going next. Okay, we figured out what the individual object is doing, but can we take that same approach to regions of the geobelt? or families of satellites manufactured by certain companies out there, or owned by certain governments, or even based on missions. So we've got weather satellites and communication satellites and Earth observation satellites. It's other patterns come out when we start to look at different context as you cluster and group these objects together. John,
Okay.
if you want to talk more about this is really more your domain, talking about the ecosystem approach to looking at
John, I would say jump in if you have anything to add, and if not,
Yeah,
I'll
no,
advance on to the next.
absolutely. Well, it's just what Tim said. It is, construct, slicing up. So the Space Force had us initially looking at the geosynchronous belt, but you could apply this to the other orbital regimes as well. But within the geo belt, as Tim mentioned, satellites are assigned to an orbital slot or a longitude above the Earth. So we've looked at the various different orbital regimes. They have their own patterns of life. The ecosystems of missions for objects and the countries of origin, et cetera. And so, the ecosystem approach benefits from grouping like objects together and getting the benefit of statistical analysis in order to identify and distinguish patterns of life in various different contexts.
Wonderful. Okay, well, let's go on to the next one then. And I think we had 8 slides altogether. So this is the event log format, and this probably illustrates a little bit more about how this data is actually stored. And again, the audience needs to keep in mind that this is probably a collection of data feeds from different systems, many of them, as you've mentioned, many of them legacy systems. So you guys are pulling together a lot of data from a lot of different sources.
Absolutely. We get observation data. We get weather data, we get space environment update data. All of this is related to the problem of trying to figure out where are the breakpoints occurring between these patterns, or where can we isolate these patterns into patterns of interest. And it basically all boils down to these 3 key ingredients. We need to have a timestamp when something occurred. We need to know when it started or when it stopped. We need to know what changed and then how it changed. And those 3 essential elements of information is basically what goes into John's process mining service that turns around these process models that describe what that ecosystem looks like, or what steps or what patterns these objects go through in their normal day-to-day. It's as simple as this, really. But getting to this point is a bit tricky. There's a lot of data fusion. There's a lot of data mining that has to go on. And then there's a lot of sophisticated analytics services behind the scenes working with this really dirty data, that this satellite observation data for its locations, and then being able to tease out these subtle differences or changes to the pattern that we use to populate these event logs.
Right. And if you could go to the next slide, please.
Absolutely.
Tim,
Absolutely.
There's an example here. So referencing the previous slide, you need 3 things. You need, in order to do process mining, you need a process case, you need an activity, and you need a timestamp in order to order everything temporally. And for this analysis, the process case that we are using is the individual satellite. For folks in the audience that might be unfamiliar, but every single satellite has a NORAD identification, a unique identifier for that individual satellite. So that is the process case. And if you think about it, back to the original use case for business process mining, if you're in a manufacturing example, the process case would be like the individual part that is being manufactured, and that part, I don't know, first some metal gets stamped and the metal gets formed into some kind of a shape, and on down the assembly line until you produce a screw. And then that would be like a single process case. Another one that I like to use for like a pattern of life thing would be a person's morning routine. If you could somehow observe people When they wake up in the morning, they wake up, they get out of bed, they perhaps use the restroom, maybe they take a shower, they brush their teeth, they have their breakfast, and they go on with their day. The individual person in that instance would be the process case. And then those activities that I was just mentioning, those would be like morning routine process activities. And if you were able to observe a dozen or 100 people in their morning routine in such a way, then you could model a process like we've been describing. But here's a example, right? So there's 3 different process cases in this example. There's 5 different activities, and we've just labeled them A, B, C, D, and E. And if you look at process case number 1, you'll observe that the activities happen in natural order, A, B, C, D, E. But then if you look closely at process case number 2, activities C and B happen in a different order than the natural order, which is interesting, right? And then if you take a look at process case number 3, everything goes along as you would expect, but then activity D repeats itself before concluding with activity E. And so what the process mining algorithms do is they interrogate these process mining event logs at scale, for dozens or hundreds or thousands of satellites as we've been analyzing them. And it produces these process models like you see here in this example. So the process in this case can go from activity A, sometimes it goes to activity B, sometimes it goes to activity C, and those can happen in different orders. And then occasionally activity D repeats itself before concluding with activity E. And all of this, of course, comes with descriptive statistics that describe the process in greater detail. And all of this can be used by the Space Force to understand what is this object doing now, and what is it likely to do next? And then even that, what is it likely to do after that, so that they can get ahead of and stay ahead of bad guys on orbit.
Awesome. Well, okay, let's go on to the next one then. So we've done process mining from event logs. Let's go to the operator engagement. So this looks like this would be kind of what the operations view would be, right? If someone was logged in looking at the screen or
That's exactly right. You got to tell the story, right? Operators don't want to look at spreadsheets and data tables and things like that. What they want is something that delivers the context of the situation of the environment, what's going on, these very complex ecosystems, I might add, and then sort of breaks it down to what's important. So for space operators, and this is just a prototype, because the eventual location for POMAT will be on other government systems working with other government data. This was just more of a proof of concept for us to be able to take observation data and then derive these process models and these patterns of life. So we would begin on the left-hand side, and just as John mentioned, that every object in space has its own identifier, it has its own catalog ID, if you will. So this particular one, 40258, is very interesting to the DoD because it has a very long and rich history of doing some very interesting maneuvers out in the geobelt, where most systems are very sedentary. Most communications and weather and the like just kind of sit in their slot and don't move a whole lot. But this particular object, and you can look at this up online, there's a lot of history on 40258, which we call the Luch, which is a Russian system. Looking at its past patterns of life, you can see in the center of this slide, it kind of depicts what it's been doing over the past year and a half. So the top graph here you see is its orbit location on the Earth. And the lines that you see behind it are its movement tracks across the Earth, over that year and a half time frame. So giving someone some perspective on what its pattern of life has been around the Earth is extremely informative, because it tells us this thing is going to where it wants to do something important. So where is that occurring? And we can find out, sort of tips their hand a little bit about where important activities are occurring around the world that they're interested in, because they're sending this satellite to go look at either a spot on the Earth, or maybe they're looking at some other objects in orbit and then trying to derive some intel there. So very important to give them some context on where these events are occurring. And then if you look below that, we're giving you a peek into its pattern of life. So its latitude, its longitude, and its altitude are changing through the year. And especially this altitude, so it goes out away from the Earth, or it comes back closer to the Earth. That's how it moves around the geobelt from one slot to the next. So the more altitude it raises, then the faster west it moves, relative to someone standing on the Earth. Or if it, decreases its altitude, then the faster it starts to move east, around the geobelt, changing its longitude. So we're tracking that, and we're giving operators some context about when these maneuvers occur, what's the frequency they occur, and what's the, some other analytics about how fast do they occur, for example, because all of this sort of describes, how urgent is this mission, how important is this mission.
Well, you just touched on some really important points, I think, related to the defense aspects of this, but let's come back to those. Let me go to the next slide first, and then we can come back and talk about some of the other aspects of that. So the next slide here is the expanded POMAT focus. Can you give me a little bit of info on this one?
Oh, so I mentioned earlier that it's a prototype service. And the great thing about building a prototype is you learn things you didn't necessarily know when you started. So we started to see patterns within patterns. So for example, if you are in your slot and you're stationary, and then you move out from the geobelt and you do a westward movement, and then you come back to a new slot in the geobelt, there are sub-patterns within, say, those transition periods that can tell us, hey, what type of thruster did they use? Or what kind of prep had to go into? Did we have to reorient the satellite a different direction in order to, get one of its thrusters to fire in a new direction? Because all of those activities tell us what's going to happen next after you've seen them enough times. So, we sort of went to the whiteboard and got our markers out and said, okay, if we're looking at this sub-pattern sort of approach to this, and you can kind of see it in the center bottom of this, where level one is just, hey, we're seeing a satellite that's doing station keeping maneuvers. It's just kind of sitting in a fixed position on geo, and it's doing its job, it's doing its thing. But when we start to expand out on maybe some of these slight changes it's making in its pattern of life behaviors, we can say, hey, this thing just did a flip, because we can see other parameters have changed in the process. And we can go even further into a maneuver like that and say, well, when did they start that flip? How long did it take to execute that flip? What thrusters were used in executing that maneuver? So this is just the tip of the iceberg, and that's what the sort of left and right columns are starting to tell us. Hey, we can start to understand these patterns of maneuver intentions, because they're orienting their craft in a certain way. We can start to determine what type of limitations and capabilities they have, technically. Based on types of thrusters they use, or how big their antennas are, their solar panels, how much power are they generating to do a maneuver like this, and so on and so forth. So that's what all, these are sort of expanded opportunities we have to learn more about not only the activities in geo, but what's the technology that's making this all happen. And then ultimately, and this is the big foot stomp, why is this happening? That's a very tough question to answer. We know what's happening because we can see it. We can kind of get after how it's happening because we understand how technology works and how space works. But that why is key, and that why is hard. And, POMAT will sort of nip around the edges of why. It's not going to solve the why. But, this in conjunction with a bunch of other services they have gets us closer to more understanding why things are happening. And that's sort of the holy grail in the data world. If you're doing predictive behavior analysis, and what it all means is answering that why question.
Absolutely. So let me see. I think that was the last slide. So let me stop the share and we'll go back. So I think that the takeaway here is that you guys are really analyzing the space ecosystem. And I think there are a couple of really key points that interest me. One thing that this has been a learning experience for me. Space is no longer a safe haven, right? Now, that doesn't mean that everything is in danger all of the time, but it does mean that there are a lot of different countries up there, and they all have defense aspects to their missions, right? And so you've got your civilian satellites, and you've got stuff going up in space all of the time, like Starlink, where they're deploying stuff, and but you also have lots of defense satellites, and they are moving around and doing independent activities. And sometimes those are adversarial, I guess. Maybe that's the best word.
Absolutely.
Yeah.
So that's what we're trying to do, is figure out what our adversaries are up to, and be able to anticipate behaviors, be able to take mitigating steps, right? So if we don't want to be observed, for example, if we knew several days out that something was inbound, right? We can track this. We know where it's going. So maybe we reorient ourselves, or maybe we move. As sort of this cat and mouse kind of activity going on. That gives us a bit of an edge. And you're right. It's becoming a level playing field in a lot of aspects out in space, where we used to be the dominant country out there with the best and most robust technologies. And that's not the case always.
Yeah,
John, did you have a thought on that?
Yeah, absolutely. And just as Tim was saying, the unipolar moment where America was the dominant country is over, and the technologies that we have enjoyed, or have had a operational monopoly on, we no longer have an operational monopoly on them, and so we are finding ourselves having to retrofit security onto technological platforms that we didn't have to have just a few short years ago. So all of this is going towards being able to mitigate risk, and not just in space, but globally, for everything that is of interest to the United States and the entire Western project.
And here's where other companies should be getting excited, because the problem we have in space is the same problem we have in smart city and smart agriculture and so many other industries out there. There's typically a lot of data already available. There's data you can get access to. It's not necessarily expensive or exquisite or even all that complicated. It's just, in many cases, so much of it. It is hard to find the signal in the noise. That's why companies like mine, that I'm not a space company, I'm a data analytics company. John is not a space company, he's a process mining company. That's how we get to play. That's how we get a seat at the table, because we've got tools that can take all this data that's literally hitting the floor and nobody's able to do anything with it, and then give it to the developers and give it to the data scientists and give it to the creative thinkers out there, and let them see what they can derive from it. Using tools. Many of the tools we use, they're highly customized, obviously, but their foundations and roots and origins are in the open source world.
Right. Tim just really rang a bell there, but there's a huge growing open source data analysis movement happening. It's been available for some time, but only relatively recently are people starting to sit up in their chairs and pay attention to the open source data that are available and what can be done with it. So everything that we've been talking about here, we used open source data for all of this, and we're able to provide some really interesting results that are not as finely tuned as the exquisite intelligence data that are available to some national security players, but clever analysis with open source data, you can really do a lot with it. And so the other open source, Twitter, you can subscribe to the Twitter fire hose and get all kinds of interesting information from Twitter. My brother is a civil engineer in Texas, and he was just telling me that there is open source LiDAR data, which is like ground penetrating coverage data or something like that. Tim, you may be more familiar with LiDAR data than I am, obviously, but it's amazing all of the data that's available that you can do really valuable analysis with these days.
Yeah. Well, and it sounds like that's where the artificial intelligence aspect of this comes in, right? And yeah, I believe you'd mentioned using something like petabyte scale cloud computing, and when you get to that scale of capacity, to me, that's an indicator that there's a lot of data that needs going through for these patterns.
Right. I'll turn it over to you just to say, all of this is open architecture, up in the AWS cloud, where you have all kinds of capability of spinning up parallel systems in order to analyze massive amounts of data. And so, yeah, what was available only to data scientists on huge mainframes just a few short years ago is available to just about anybody with a credit card and a couple $100 credit line.
Yeah, yeah.
Yeah, and Tim, that's a great point you brought up about the introduction of artificial intelligence and deep learning and machine learning, and how do we sift through all of this noise to find the signal? It is well beyond, the human ability to recognize these patterns and where they're occurring. And a good mathematician, a good software developer that's got just a basic understanding of machine learning or data fusion. There are some off-the-shelf tools that get you started, and can lead you down a path that enables you to become highly specialized in understanding how to find this particular pattern. Because I guarantee you, there's a need for that out there somewhere. Someone's got data that can, and they need a problem to be solved. So that was a huge technical leap forward when a lot of these AI tools and these analytic tools started to hit the open source market, and the creative thinkers, like I said, I'm convinced, the next big innovations are coming from clickbait ad builders in their basement at the moment. Those guys and gals are learning things differently than we learned them, and becoming very resourceful and very creative in how they apply these solutions to modern day problems. It's exciting to watch mature.
If it's okay, I had another use case that kind of came to mind for this. And this was something I was wondering about. So in addition to threats on orbit, again, from adversarial satellites, there's also this possible threat on orbit from space junk. And that's something that's been in the news a lot more lately. So with regard to that, I guess, is that something that your system could predict and provide possible collision alert or warning signs? If a satellite is making maneuvers, right? If the Space Force is looking at moving things, is your system able to go through and say, no, this is bad, this is putting it into path that will cause damage to it?
100%. There are some large government organizations around the world that are really concerned, and big insurance companies as well, that are underwriting a lot of the commercial progress that's being made, are highly concerned about what we call conjunctions. That's when two systems come in close proximity to each other. And then when you've got other bad actors out there, lighting off ASAT, anti-satellite systems that create these debris clouds, and clutter up, some of these, very populated belts, low Earth orbit, mid Earth orbit, and geostationary. Tremendous concern, and it's not just a DoD concern, right? There's a lot of commercial companies out there that, their whole business structure is built around their system, their satellite providing, communication coverage. So tremendous interest in this, and interestingly enough, the DoD, who used to have the preponderance of systems and oversight of what's going on in space, is migrating to the Department of Commerce. Mm-hmm. So now you're standing up this whole new organization to take on that challenge. And then be able to, just like we provide weather services around the world, is also be able to provide these conjunction analysis and help make space a safer place. And tools like POMAT are perfect for this, because we can do not only this, this predictive behavior of when things are going to maneuver, but we can also do analysis of, say, hey, when something moves, here's what it's going to be next to 5 days, 10 days, 12 days out. And then be able to take some necessary precautions to be able to, make sure that things don't come too close to each other. And we can also observe things like rocket bodies and old defunct satellites, and keep an eye on their activities to make sure that, number one, they are dead, right? They're not just a zombie satellite. That happens. But that they don't pose a threat, that their activities are benign, or they're in a location where they're not going to threaten anybody. And anybody who can read, the POMAT dashboard, like we just showed, could use that as a planning tool to ensure that their systems are out of harm's way. Or when they become in harm's way, we've got enough mitigation time in front of us to take necessary steps.
Wonderful, wonderful. Well, gentlemen, thank you so much for your time. I can't thank you enough. It's amazing to be able to showcase this for the audience. So let me close by asking, what comes next for you guys? Where can we see you in the very near future in the headlines?
Oh, we want to commercialize this service. DoD is great. They're a tremendous, awesome customer. We love the challenges they pose to us. But just as space is going global, these problems are going to get harder, and there's going to be more of them popping up. And we're going to be more and more reliant on companies like mine and John's that can, we're data wranglers that can, make sense of all this data. Like I said, that literally hits the floor and can turn it around really rapidly and make it actionable and make it profitable. So that's the good part. One of the great things about this particular DoD program we're under is that there's a heavy emphasis on commercialization of the services we're building. So we as a company, we're not just stuck in this government contracting role. And then we continue, because we're commercially focused, we're continuing to upgrade and develop it and make it better, stronger, faster. And then it's the win-win for, the DoD, because, it's sort of seed funding they gave us to get it started, but then, the demand and the traction we get from it in the commercial sector ensures that the DoD investment continues to get better over time.
Yeah, totally agree. Tim mentioned insurance just a moment ago. We perceive great value to the insurance industry for this kind of a capability. The commercial manufacturers of satellites and the owners of the satellites, the ones who are paying for this expensive piece of hardware to do something on orbit, they insure it for various different performance reasons. And when an insurance company has to pay out for some reason, they are wanting to investigate, is this was the satellite operating as it should? Was it being operated as it should? And that type of forensic analysis of satellite behavior could be extremely valuable to the insurance industry. Is like, I don't know, you guys said you ran out of, you were supposed to have like a 20-year life cycle, but you ran out of gas after only 5 years. And they say, well, we were operating it normally. Well, according to our analysis, it looks like maybe you were like doing some stunt flying up there and you were burning fuel at an unusual rate. I'm not so sure we're going to pay out on this insurance claim. So that would be something that would be extremely valuable, I think. But when we asked the Space Force gang about this, they asserted that any company that is operating in space should be interested to be aware of what is happening in and around their valuable space assets. So any commercial company that is operating up there, should want to know about the space domain awareness immediately around their valuable assets. So this is a tool for doing that. And then on top of that, there is an increasing demand for like an always on service that is continually consuming information and producing insights. And this kind of a service is that in the space domain, but it could also apply to other domains of interest.
Wonderful, wonderful. Well, gentlemen, thank you both. Thank you both for your time today. Thank you both for your past service in the military and your continued service helping to track and safeguard our national security in space.
It's a pleasure, Tim. It really is.
Thank you. Thank you, Tim.